So it's been really wonderful seeing everyone commingling and meeting new people and the vibrant discussion, which is really, really exciting. We're now going to move on to the next stage of the symposium, and we're going to continue with the last of the presentations on research. And for that, we have Professor Michael from Monash University. However, until recently, and still currently has a part-time appointment at Manchester University in the UK. That's partly justified. He's also the Director of Research Infrastructure at Monash. He's moved to Australia only about 2 years ago from Manchester, as I was saying, and in the UK, which is where I first met Michael, he's very renowned for having built a collegiate, supportive, and very productive community of researchers on zirconium for the nuclear industry. Now, zirconium is a very important metal for the nuclear industry, as I'm sure you'll hear about it. And really, the community of zirconium research in the UK went from hardly anything at all to being one of the most internationally recognized communities. And that was largely due to the many centers, program grants, and other things that Michael and his co-workers have led. So he really had a pivotal role in that transition. And I'm hoping that he will tell us here in Australia how we can do something similar. Please welcome Michael on stage.
Thank you, Patrick, and thank you for the kind introduction. So I'm very happy to be here today. I should say I moved to Australia not with the intention of continuing work on nuclear materials, but of course this has changed now. So we will see how we go with this. So as Patrick said, I was part of the group of academics in the UK redeveloping the nuclear skill set in academia, particularly in my case materials. And I was spearheading the zirconium research activity. So we will talk a little bit about this. So I'm going to talk a little bit about structural nuclear materials. So we've heard quite a bit about fuel, some mentioning of zirconium. Some people might wonder here why zirconium. We can touch on this briefly. So we'll go and see, what we can find out here. So I thought I don't quite know what is the background of all the people here. So I thought I'd just give you a few facts about structural materials for light water reactors. So what we find in those reactors is mostly steel. We find zirconium alloys, and we find a little bit of nickel alloys as well. Zirconium alloys, it's a bit of a peculiar metal. It's very similar to titanium. So I came into this business because I actually had a strong background in titanium alloys. I was working with Rolls-Royce on the aero engine side. And zirconium is extremely similar, but obviously operates in a very different environment. And the reason why zirconium is used, it's essentially transparent to neutrons. So it lets neutrons through very easily. And because you produce neutrons, so you need a material which doesn't capture the neutrons. So these are the very important structural materials in the nuclear reactor. The other important aspect is you really need to understand corrosion. Aqueous corrosion is very important in this environment. So Manchester, when we started again to work in nuclear, became quite powerful in this area, and it was simply based on the fact that Manchester is very strong in metallurgy and is very strong in corrosion. That is the quintessence if you want to get into this business. And it's really quite pleasing to see now when, now I'm based at Monash, and we have a world expert in steel with Chris Hutchinson. We have really good people in corrosion like Zeb Thomas, and I might be able to contribute a little bit on zirconium as well. So the other thing is irradiation damage, of course, but this is actually particularly important in terms of structural materials for the fuel cladding. Stress corrosion cracking is a very important issue. especially in connection with welds. And there's a lot of stress corrosion cracking expertise here in Australia already. So there's, again, transferable skills. And then it's important to understand, the reactor needs to last, on the civil side, we are talking about 60 years plus. People really hope that these new reactors, which are currently built, will actually last 100 years. They're very expensive to build, as I'm sure you're aware. While fuel assemblies are really a consumable. They only stay in a reactor for 1.5 years. But the issue with that is, when we take them out, there's still fuel in there. So it's like, you take your car, you drive around, you go to the petrol station, you still have 40% of your fuel left, you dump it, and you refill your car. That's what we do at the moment with the fuel. So that's why we really need to also understand the fuel cutting much better, and the fuel, of course. So an important aspect here is that when you now connect this to manufacturing, advanced or high-value manufacturing is not just about getting the material into the right shape. It's actually also understanding the material, how it performs in this environment, which is a very, very demanding environment. And in the case of the reactor itself, it can't be easy, things can't be easily replaced. So now we are here particularly because of AUKUS. We've heard this a lot. And so in principle, we are here more about, because of the submarine side. So what is different? What is different between a core in a nuclear submarine and a civil nuclear reactor? Now, we don't know all the details because it's classified. I've worked with Rolls-Royce many, many years, and but I haven't been cleared. And if I was, I wouldn't be able to talk about this here anyway. But it's clear it's a very small PWR core, so pressurized water reactor. It has a very different fuel design. And this is really because, remember, a submarine needs to accelerate and decelerate all the time, whereas a civil nuclear reactor always runs at a constant level. And so that means you have a different fuel and you have a different design. They still use zirconium to encapsulate it, but the fuel is somewhat different. And the design itself, it's very different overall. Now, the fuel now has a lifetime. Well, sorry, the submarine is supposed to last 25 years. I'm sure when we get to 25 years, there will be a lot of discussion, can we extend the life? Because these things are very, very expensive. Now, here, the fuel assembly is not a consumable anymore. The fuel assembly stays in the reactor, in the machine, until we decommission the submarine. So it's a very that puts a lot of more focus on the fuel here, in this case, in the fuel assembly. And one might say, although I don't want to indicate in any way that this is, that the safety is not taken very, very seriously here, but it's less regulated than the civil nuclear space. You have small problems in a civil nuclear reactor, and the reactor will be shut down. You might not have that here in this case. So just also to emphasize, a submarine, at least the one we are talking about here, has a Generation 3 reactor. It has an environment which is very similar to PWRs. Civil PWRs is very different from Generation 4. So I think it's important to realize that 20 years ago in the UK, all the nuclear expertise had actually disappeared. As you might know, that the UK decided in the late 80s to stop building, or in the 80s, to stop building new nuclear power stations. And a lot of the nuclear experts in academia, they left the UK. I remember when I started to work on it, I met a lot of people from Canada, from the US, all speaking with a British accent, much more than me. Well, I always confused them. So so there was very little left in the late 90s. And so this all had to be re-established because it was clear there was a new nuclear renaissance coming to the UK, but also because there were actually a lot of nuclear power stations which still had to be maintained. The challenge for the UK has been that the UK has actually not, they only have one PWR, everything else are advanced gas-cooled reactors. It's a very different type of nuclear reactor. So the UK also had to develop, and is still in the process of developing, the right expertise for water-cooled reactors. And so in the last 20 years, there has been a lot of activity in the UK in terms of research, and it has become a very, very lively and exciting place to do this kind of research. So I just want to give you a few examples of what we achieved in the last 10 years, 15, 20 years. And this is particularly related to what I've been doing and leading. So we actually had a very large, essentially a center of excellence in the field of new nuclear manufacturing. And the reason why I bring this up, because I believe there are a lot of people here interested in manufacturing. The interesting thing here was that joining, so welding is a really important part. Joining in nuclear is not very advanced. It's using very conventional welding techniques. So doing research in this field often means you try to introduce welding techniques which are already established, let's say, in the aerospace sector, but not yet in the nuclear sector. Machining is an important aspect because you want to machine fast, but if you alter the surface of your material and then it shows more stress corrosion cracking, you have a problem, or it alters the corrosion properties. And also hot isostatic pressing is actually of great interest, especially in relation to small modular reactors, because everything is a bit smaller, so there are a lot of more components which could be manufactured in this way. And then the thing I really want to highlight is that a program like this cannot just look at manufacturing itself, but it has to look at how the manufacturing affects the properties of the material. Right? This is absolutely crucial, and this is what manufacturing makes advanced. Advanced manufacturing is not just using new manufacturing techniques, but it's also about really, truly understanding how the manufacturing affects the properties and the performance of the material and the component. Then going to the zirconium research, so Patrick has already mentioned that essentially 20 years ago, there was not a single academic in the UK working on zirconium alloys anymore. So here I just show you how over 15 or a few more years, we developed, with many different research projects, starting small and growing. And so this is EPSRC, which means research council like ARC. They put a lot of money in, a lot of international collaborations. The Research Council was very concerned that we would try to reinvent the wheel. They wanted us to work internationally, and also industry. So we got a lot of industrial support, Westinghouse, Rolls-Royce, and so forth, who got involved with us. And they were really excited to work with us. They actually preferred to work with us because they felt that the national labs, for instance, in the US, are not as agile as UK universities. So we have to be agile to be attractive. And that eventually, on the zirconium side, led to a center of excellence where we brought everything together, looking at the different degradation modes, not in isolation anymore, but together. And Patrick is actually, so it's a very inclusive community. We've brought people in. We can't provide funding for them, but people who work in this field, they can be part of the club. And therefore, nobody works in isolation, and we can take this field forward much more quickly. And so Patrick, for instance, is part of this community as well. So I think key to the success of what we have achieved in the UK, and which what I'm hoping we can now achieve here in Australia as well is we have to work in collaboration in academia. We must not work against each other. I think Ed has already mentioned it, there's so many opportunities. There's no reason that we feel we have to compete. And in fact, the people here who work in this field at the moment have all very complementary expertise. It is absolutely crucial that we form a seamless team with industry. And I think we will have, we want to develop the expertise in Australia, but we have to do it with people from outside Australia. There's just no other ways of doing this. And that is also something that happened in the UK. As academics, we want to do world-class research. And therefore, we need world-class research facilities. And we need to combine the experimental work with the advanced modeling tools, computational modeling tools, to really provide understanding. This is what we can do in academia. We can just a second. We can tell the industry what works and what doesn't work. And important is that in this business, the regulator, when industry goes to the regulator and says, oh, we have a better product here, the regulator will ask industry, why do you think this is better? And if industry cannot answer the question, they cannot use this new material or this new manufacturing route. And that's really important. And just to close this, the strong expertise in metallurgy and corrosion is absolutely critical for this kind of field of structural nuclear materials. And I think that's it. Yes, thank you.